Solid-state relays with inverse time curves are commonly used as replacements for electromechanical trip units. They offer improved accuracy, stability, and flexibility. When undertaking such a replacement, there are several key considerations. Firstly, compatibility. Ensure the solid-state relay you choose is compatible with the DSL power circuit breaker. Secondly, function settings. Carefully set the inverse time curve parameters to match the desired protection characteristics. Incorrect settings can compromise circuit protection. Verify that the solid-state relay's voltage and current ratings meet or exceed the circuit requirements. The solid-state relay should provide adequate isolation between the trip unit and the circuit. Several NEC and ANSI standards are relevant to this type of modification. NEC 240.2 states that circuit breakers must be listed for use in the intended application. ANSI/IEC 37.13, the standard for AC power circuit breakers, specifies test procedures and performance requirements for circuit breakers. ANSI/IEC 37.90, the standard for relays and relay systems associated with electric power apparatus, provides guidelines for solid-state relays used in power systems. When implementing this modification, consider these points. Follow manufacturer's instructions for wiring the solid-state relay to the circuit breaker and power source. Calibrate the solid-state relay according to the manufacturer's specifications to ensure accurate protection. Perform thorough testing to verify the proper operation of the solid-state relay and the entire circuit. Update the circuit documentation to reflect the modification and include details about the solid-state relay. Consider using a solid-state relay with adjustable time current curves to provide flexibility in protection settings. Monitor the solid-state relay's performance over time and make adjustments as needed to ensure continued reliability. A qualified electrician or engineer familiar with circuit breaker modifications can provide assistance. The project requires a methodical approach. The initial step involves a thorough assessment of the existing Westinghouse DSL power circuit breaker. Collect all relevant information, including the breaker's model number, voltage rating, current rating, interrupting capacity, and the settings of the existing Digitrip RMS 610 trip unit. Document these settings carefully, as they will serve as a baseline for configuring the replacement solid-state relay. Selection of the appropriate solid-state relay is critical. Consider factors such as the breaker's voltage and current ratings, the desired protection characteristics, and any specific requirements of the application. Ensure that the solid-state relay is compatible with the breaker and that it meets all applicable NEC and ANSI standards. Several manufacturers offer solid-state relays specifically designed for circuit breaker protection. Compare the features and specifications of different models to find the best fit for the project. Once you have selected the solid-state relay, carefully review the manufacturer's instructions for installation and configuration. Pay close attention to the wiring diagrams and any specific requirements for connecting the relay to the breaker. Before beginning the installation, to energize the circuit breaker and lockout-tagout procedures to ensure that the power is completely off. Disconnect the existing Digitrip RMS 610 trip unit from the breaker. Carefully label all wires before disconnecting them to avoid confusion during the installation of the solid-state relay. Install the solid-state relay according to the manufacturer's instructions. Ensure that all connections are tight and secure. Pay close attention to the grounding requirements and any specific instructions for connecting the relay to the breaker's trip coil. Once the solid-state relay is installed, configure the inverse time curve parameters to match the desired protection characteristics. This involves setting the relay's time dial, instantaneous pickup, and other settings according to the documentation of the previous trip unit and the new relay. Use appropriate test equipment to verify the settings of the solid-state relay. This may involve injecting current into the relay and measuring the time it takes to trip the breaker. Compare the test results to the desired protection characteristics to ensure that the relay is properly configured. After configuring the solid-state relay, perform thorough testing to verify the proper operation of the breaker. This may involve using a circuit breaker test set to simulate fault conditions and measure the breaker's tripping time. Compare the test results to the manufacturer's specifications to ensure that the breaker is operating within acceptable limits. Document all steps taken during the replacement process, including the settings of the existing trip unit, the specifications of the solid-state relay, the wiring diagrams, the configuration settings, and the test results. This documentation will be valuable for future reference and troubleshooting. Update the circuit documentation to reflect the modification and include details about the solid-state relay. This will help to ensure that the circuit is properly maintained and that any future modifications are made in accordance with the original design. During the replacement process, it is helpful to consult with a qualified electrician or engineer who is familiar with circuit breaker modifications. They can provide valuable guidance and assistance to ensure that the project is completed safely and successfully. In addition to the steps outlined above, consider these additional tips. Use a solid-state relay with adjustable time current curves to provide flexibility in protection settings. This will allow you to fine-tune the relay's settings to meet the specific needs of the application. Monitor the solid-state relay's performance over time and make adjustments as needed to ensure continued reliability. Solid-state relays can drift over time, so it is important to periodically check their settings and make adjustments as necessary. Consider the ambient temperature in which the solid-state relay will be operating. Temperature can affect the performance of electronic components, so it is important to choose a relay that is rated for the operating temperature range. Ensure that the solid-state relay is properly ventilated to prevent overheating. Overheating can damage the relay and reduce its lifespan. Use surge protection devices to protect the solid-state relay from voltage spikes. Voltage spikes can damage electronic components, so it is important to protect the relay from these events. Use a high-quality solid-state relay from a reputable manufacturer. This will help to ensure that the relay is reliable and that it will provide years of trouble-free service. The selection of an appropriate inverse time characteristic is crucial for optimal circuit protection. Several inverse time curves are available, each with its own unique characteristics. The choice of curve depends on the specific application and the desired protection characteristics. Common inverse time curves include moderately inverse, very inverse, and extremely inverse. A moderately inverse curve provides a moderate amount of time delay for overcurrent conditions. It is suitable for applications where a moderate amount of coordination is required with other protective devices. A very inverse curve provides a greater amount of time delay for overcurrent conditions. It is suitable for applications where a high degree of coordination is required with other protective devices. An extremely inverse curve provides the greatest amount of time delay for overcurrent conditions. It is suitable for applications where the highest degree of coordination is required with other protective devices. The selection of the appropriate inverse time curve should be based on a thorough analysis of the circuit and the desired protection characteristics. Consider factors such as the fault current levels, the coordination requirements with other protective devices, and the potential for nuisance tripping. A qualified electrician or engineer can provide valuable assistance in selecting the appropriate inverse time curve. The calibration of the solid-state relay is essential for ensuring accurate protection. The calibration process involves adjusting the relay's settings to match the desired protection characteristics. The calibration should be performed according to the manufacturer's instructions, using appropriate test equipment. Common calibration procedures include setting the relay's time dial, instantaneous pickup, and other settings. The calibration process should be documented carefully, including the settings of the relay and the test results. This documentation will be valuable for future reference and troubleshooting. The testing of the solid-state relay is necessary to verify its proper operation. The testing should be performed after the relay has been installed and calibrated. The testing should be performed using appropriate test equipment, such as the circuit breaker test set. Common testing procedures include simulating fault conditions and measuring the breaker's tripping time. Test results should be compared to the manufacturer's specifications to ensure that the relay is operating within acceptable limits. The test results should be documented carefully, including the test conditions and the measured values. This documentation will be valuable for future reference and troubleshooting. Proper documentation is essential for maintaining the circuit and ensuring that any future modifications are made in accordance with the original design. The documentation should include all relevant information about the circuit, including the breaker's model number, voltage rating, current rating, interrupting capacity, the settings of the existing trip unit, the specifications of the solid-state relay, the wiring diagrams, the configuration settings, and the test results. The documentation should be updated whenever any modifications are made to the circuit. The documentation should be stored in a safe and accessible location. Regular monitoring of the solid-state relay's performance is important for ensuring continued reliability. The monitoring should include checking the relay's settings and verifying its proper operation. The monitoring should be performed on a regular basis, such as monthly or quarterly. The results of the monitoring should be documented carefully. If any problems are detected, they should be addressed promptly. Regular inspections of the circuit breaker and the solid-state relay are important for identifying any potential problems. The inspections should include checking for loose connections, damaged wiring, and other signs of wear and tear. The inspection should be performed on a regular basis, such as annually. The results of the inspection should be documented carefully. If any problems are detected, they should be addressed promptly. When replacing the Digitrip RMS 610 with an external solid-state relay, understanding the existing system's parameters is essential. The RMS 610 provides both long-time and short-time protection functions, typically designated as long-time pickup, long-time delay, short-time pickup, and short-time delay. These parameters define the overcurrent protection characteristics of the circuit breaker. Firstly, long-time pickup refers to the current level at which the breaker will begin to trip after a specified time delay. It is typically set as a multiple of the breaker's continuous current rating. Secondly, long-time delay refers to the amount of time the current must exceed the long-time pickup setting before the breaker trips. This delay allows for temporary overloads, such as motor starting currents, without causing the breaker to trip unnecessarily. Thirdly, short-time pickup refers to the current level at which the breaker will trip with a shorter time delay than the long-time function. It is typically set higher than the long-time pickup setting to provide faster protection for higher fault currents. Fourthly, short-time delay refers to the amount of time the current must exceed the short-time pickup setting before the breaker trips. This delay is shorter than the long-time delay and is intended to provide faster protection for more severe fault conditions. When selecting and configuring the solid-state relay, these parameters must be carefully considered to ensure that the replacement relay provides equivalent or improved protection. The solid-state relay should be capable of replicating the long-time and short-time functions of the RMS 610 with adjustable pickup and delay settings to match the existing system's characteristics. Ensure that the solid-state relay has sufficient interrupting capacity to handle the fault currents at the installation location. Consider using a solid-state relay with additional protection functions, such as ground fault protection or undervoltage protection, to enhance the overall protection of the circuit. Follow the manufacturer's instructions carefully when installing and configuring the solid-state relay. Use appropriate test equipment to verify the settings and operation of the relay. Consult with a qualified electrician or engineer if you have any questions or concerns. Remember to document all changes made to the circuit breaker and the protection settings. This documentation will be valuable for future reference and troubleshooting. Regular maintenance and testing of the circuit breaker and the solid-state relay are essential for ensuring continued reliability.